Continuing 1.7, an extremely useful type of indirect proof is known as proof by contrapositive. Again, we're still if then. If you want to do a proof by contrapositive, negate Q implies the negation of P, and that's sufficient to prove if P then Q. So, if the original statement is if it rains, then there must be clouds, the contrapositive to that would be if there are no clouds, then it's not going to rain or it can't rain. This type of proof right here, Vegas proof, that is, if P is not true, then whatever the outcome is, we assume that's true. Q is always true. So we're trying to check if it rains, then there must be clouds. If it doesn't rain, there could be clouds, there could not be clouds. You can't make any conclusion. If the if statement is false, the outcome is true regardless. Trivial proofs are those that you could pretty much show P implies Q really easy. Show if P is true, Q falls right out of it. So those are trivial. We're going to do some of each today. I want to specify what an irrational number is. A real number is rational if there exist two integers P and Q where Q doesn't equal 0 such that this rational number can be written as the quotient of those. A real number that is not rational is called irrational. So irrationals are like e to the 1, e to the second, the square root of 2, square root of 3, a log of 3, 2, so on and so forth. The pi. Proof by contradiction. Proof by contradiction, again, remember, we're trying to show this. Proof by contradiction, assume P and assume not Q. You're going to get a contradiction to your statement which indicates this was wrong. This was false, and then you fix it. A counterexample is when you pick one example. So if they say for all x, P of x does this, or for every x, P of x does this, all what you have to do is find one counterexample. One example in which this doesn't work for in your set. Now we're going to continue on the same page, and we're going to look at some problems and do some proofs, and we're going to try to follow how they work. So in this case, it says 10. Use a direct proof to show that the product of two rational numbers is rational. So here, let m and n be two rational numbers. Then we know that the f part, m can be written as a over b, where b does not equal to 0. Of course, a and b are integers, and n can be written as c over d, where d is not 0. So here we're saying a, b, c, and d are integers. That's by definition. Now, if I take the product, mn, that would be a over b times c over d. That would simply be AC divided by BD. But we know that BD does not equal 0. That's from the above definitions right there, right? And AC is an integer. And BD is an integer. And we know that the quotient of two integers is an integer. Therefore, this is a form of a rational number by definition. Prove or disprove. So here they're asking, is it or is it not? The product of non-zero rational number and an irrational number is irrational. So they're saying prove or disprove. Well, let's see. Let M be a rational number and N be an irrational number. So here we're going to say M is A over B, where B does not equal 0. But N, we're going to call that some letter Y. We can't call it a fraction because we know that doesn't work. It can be written as a fraction. So now, this is going to be proof by contradiction. We're going to say, so we did the if part. Suppose the product is rational. Then we're going to say M times N is going to be A over B times Y, where of course B does not equal 0, we know that. Now, we also know that B over A is also a rational number. Let me think really quick. Right, because here A cannot equal 0. If A equals 0, then you're going to get really 0 out of this product. And we're assuming that both of those are non-zero. So B over A is also rational because A does not equal 0 by that definition right there. And if I take out of those, now if I take A over B times Y and multiply it by B over A, we just did this. If you multiply two rational numbers, you're going to get a Y. But isn't Y irrational? So isn't this a contradiction? So since this is a contradiction, therefore X A over BY must be irrational. Right, so this is by contradiction. Assume the if part, prove that the then part cannot happen. The issue with you proving that you've proven it directly, then you have to take into account all of these infinite possibilities. And that's why proof by contradiction is often very useful and very efficient. So, looking at 14, prove that if x is rational, let x be rational. That means automatically that x equals some A over B, where b does not equal to 0. And since they're saying x cannot equal 0, that means a does not equal 0 because 0 over any non-zero number is 0. Then 1 over x, by definition, wouldn't this be 1 over a over b? Wouldn't that be b over a? Well, isn't that rational? Therefore, 1 over x is rational. Remember, right there, a cannot equal 0 to begin with from the beginning, so therefore, that is a simple proof. The next problem, 16. Prove that if x, y, and z are integers, okay, let x, y, z be integers. And let x plus y plus z, this sum is odd. Okay, those two. Then at least one of them is odd. Oh boy, at least one of them you have to show. One of them is odd, 2 of them is odd, 3 of them is odd. Well, let's say that, what's the complement of that? Then we say at least one, okay, all of them. Assume that, you know what, that here. Assume that x, y, and z are all even. So at least one. We have 3 of them, right? When you say at least one, you're saying 1 or 2 or 3, right? So if you negate that, you want to say, well, none of them are odd, which means all of them are even. Then by definition, we know that x equal to a, y equal to b, and z equal to c. A, b, c are some integers not equal to 0. And then x plus y plus z would be 2a plus 2b plus 2c, which is 2 into a plus b plus c, which is even. And this contradicts x plus y plus z is odd. Therefore, our assumption must be wrong. Therefore, well, we said all of them, not all of them, at least one of them. Therefore, at least one of x, y, or z is odd. Alright. How about 18? Prove that if m and n are integers, let m and be integers. So, and m times n be even. Okay, integers and even, very good. Then the conclusion, m is even or n is even. So m is even, n is even. Okay, let's go backwards. Contrapositive. So this is saying then m is even, n is even. Suppose So remember, contrapositive, P implies Q. We're going to prove not Q implies not P. Suppose N and N, it says, or right, the complement of that are odd. Then I could write M equals some 2A plus 1 and N equals some 2B plus 1, assuming A and B are integers. So if I take the product I should write it here. Wouldn't that be 2A plus 1 times 2B plus 1? Isn't that 4AB plus 2A plus 2B plus 1? Isn't that, we did this previously, right? 2 times the sum of integers and integers. Isn't this odd? And it's supposed to be even. So what does that mean? That means my assumption is false. And what was my assumption? My assumption that this or this, therefore, N or the complement of that is even. Okay, now we're looking at number 20. We have two things to worry about. It says they want us to use both. So remember, contrapositive was, again, the idea was P implies Q. Contrapositive in A was not Q implies not P. And contradiction, assume P gives not Q, and sure there's something wrong with that assumption, therefore that must be true. Well, let's do part A first. It says, let's read it. Prove that if N is an integer, if N is an integer, and 3N plus 2 is even, then the conclusion, the Q, then N is even. Okay, if we want to start this, we're going to do it using contrapositive. If N is odd, right, the complement, if N is odd, then what we want to show that suppose N is odd, then N can be written as 2A plus 1. And if I take 3N plus 2, that will be 3 into 2A plus 1 plus 2. That is 6A plus 5. So I could say that is 6A plus 4 plus 1, which would be 2 into 3A plus 2 plus 1. This is odd. And we're supposed to get it to be even, right? So that pretty much proves that our assumption is wrong. And if I go for B, prove by contradiction, suppose that 3N plus 2 is even, then N is odd. And let's do that proof. Well, if I take 3N to be even and N is odd, can't I say 3N plus 2, which is even, and add or subtract? Let's say subtract. You could add to it. Plus N, which is odd. If you take an even and an odd, you are supposed to get an odd. And wouldn't that be 4N plus 2? Isn't that 2 into 2N plus 1, which is even? Isn't that a contradiction? Therefore, the assumption, therefore, N is even. Let me get that one up. Let me fix that really quick. Okay. Prove the proposition P of 1. Let's see what it says where P of n is the proposition. If n is a positive integer, so that's the if part, then n squared is bigger than or equal to n. P of 1, where 1 is n. It says if 1 is a positive integer, and it is, then n squared is bigger than 1 squared is bigger than 2 equal to 1, which is true. Right? So this is a fairly simple and quick proof. This is the trivial case, of course. Let's use a bit of logic. Show that if you pick 3 socks from a drawer that contains, the drawer only has blue or black. So I'm picking a blue or a black. You must get either a pair of blue or a pair of black. Okay, well, suppose that if we pick 3 socks from a drawer, that's the P, containing these socks, then you will get either a pair of blue or a pair of black socks. They're saying you're going to get 2 of one of them. Let's say you will not get a pair of blue or a pair of socks, or a pair of black. Well, let's see. Then if I pick 2, and let's say I get 1 blue and 1 black, so I only have 1 of each. When I pick the third, well, isn't that going to be a blue or black? Doesn't that mean automatically, if it was the first case, I'll get 2 blue and 1 black, that's a pair, right? Or if I pick another black, I'll be getting 1 blue and 2 black. Therefore, that's a contradiction to what I just said. Therefore, you must get a pair of those. 28. Prove that if n is a positive integer, let n be a positive integer. Then it says n is even if, let n be even, oh, I'm sorry, if and only if. Okay, so you have to prove it forward and back. Even only if, you have to prove if then, and then have to switch it. So P if and only if Q. That means you're going to have to prove P implies Q, and you must show Q implies P. It works both directions. So let's do the first case. N is positive. Then we're going to show N is even. Let's assume that N is even if and only if 7n plus 4. So okay, here N, if it's even, must be 2a. If I take 7n plus 4, that will be 7 times 2n. So I'm trying to show that this is even. That would be 14n plus 4. that will be 2 into 7a plus 2, which by definition is even, it checks. But if it's an only if statement, I have to go both routes. This is not enough. Now, I'm going to go for the other piece. I'm going to say, suppose the counter is true. Suppose that 7n plus 4 is even. Of course, we're assuming n is a positive integer. Right? We want to show that n is even. Well, how are we going to show that? Suppose this is true, and then assume that n is odd. Then by definition I could write n as 2a plus 1. And if I take 7n plus 4, which is even, that would be 7 times 2a plus 1. That will be 14a plus 7 plus 4. That will be 14a plus 11, which is 10 plus 1. That will be 2 into 7a plus 5 plus 1, which is odd. That's a contradiction to what I have. Therefore, that's a contradiction to what I have. Therefore, n must be even. And that completes the contrapositive. And that concludes this section.